All right, hello everyone again. Welcome back to these Chegg office hours. This session for the next hour will be all on linear algebra. So my name is Joe. I am a fifth year PhD student at NYU, and I'm happy to be here on behalf of Chegg to help you answer all of your toughest linear algebra questions. So hopefully everyone has been having a good long weekend if you have today off. I expect tonight will be more chill night just to help you answer any last minute questions, but also I'm aware that if you're taking the linear algebra class, this might start to be the time for your first midterm if you have any. So I've kind of structured today with my prepared questions, kind of mostly focusing on a review and perhaps helping any last minute preparation for any midterms. But as always, please feel free to type in any questions you'd like me to go over in specific in the chat. And yeah, so let's get started. So actually I have here, the first question is a request from last time. Someone asked to do an example for the Cholesky decomposition. But I was thinking it might be a lot to start off with this as the first question. So I'm going to come back to it and start off with maybe a little easier of a question. And so this kind of falls more into the review of the category of midterm review questions. So I'll just get us started with this question. So it is to solve this system, this matrix equation AX equals 0. I'll always use this to write the 0 vector. And here I have written the matrix A, which is as written. Okay, so typically, how do we do this question? We would want to start off by doing row reduction. And okay, I wanted to give us an easier question. So this time, this matrix is already in row reduced form. Hopefully you can see that here I have this row. The first entry is a 1. And in that 1, every other entry is a 0. And same thing here. This row, the first entry is this 1. And everything else in this column is a 0. So that's what makes this in reduced row echelon form. And so from here, there's a standard way to solve the system of equations. And first we can write out what would it mean to write AX equals 0 with this matrix A. And it corresponds to two equations, one for each row. So the first equation is going to be x1 plus 0x2 minus 8x3 minus 7x4 equals 0. And the second row will correspond to 0x1 plus x2 plus 4x3 plus 3x4 equals 0. And so you can see how the numbers here form the coefficients here of my equation. And so what I do is I take the first pivot variable, which is what this one is called. And in the first equation, I'm going to move everything to the other side. So this becomes x1 equals 8x3 plus 7x4. And here we have the second equation becomes x2. So x2 is the pivot that I care about here. And so I'm going to keep this here and move everything else to the other side. What I get is x2 is equal to minus 4x3 minus 3x4. And then what I can add on is the fact that x3 can be any variable. So when I solve this, any column where there's no pivot, I call a free variable. So here I have x3. I write that it just equals x3 to indicate that it can be any number. And then x4 equals x4. Likewise. And so now I kind of have a form for my solution, which is that my solution is going to be this vector with 4 entries. And it's going to be something in the form of this right-hand side. I'm going to move down a little bit. Okay. And so I can write, so this is already in what's called parametric form. But usually it actually gives more information to write this exact thing in a vector form. So here I have x1, x2, x3, x4 is equal to, and then I can look at the variables I have here. So the first one is x3. I'm going to look everywhere it appears and write the coefficients. And so here I have oh yeah, from at Sale on TikTok, could you parameterize? So, well, I think I'm going to do what I consider to be writing the solution in a parametric vector form. If that's not what your question is asking, definitely ask a follow-up question that I can clarify. But this is okay. Maybe let me write it down and I'll say a comment afterwards, and then let me know if you have a follow-up question. But I'm going to take x3 and I'm going to pull it out from everything here. So what do I get? For the first equation, there was an 8. In the second equation, there was a -4, and then a 1, and then it didn't appear in the last equation. So I have 0. And then I have same thing with the x4. I got a 7 in the first equation, a -3, and then a 0, and then a 1. So I usually call this form of the solution, as parametric vector form. So depending on your, depending on the question, either of these solutions, either writing it like this or like this, would work as an answer to a test. They both describe the solution in some way. These are both called parametric solutions because you have the vector that describes the solution on the left, and on the right I have some numbers, but they're given in terms of these variables. So these are called parameters because, okay, how do I interpret this solution? How do I interpret this? It means that I can put any number I want for x3 and x4, and I can plug it in, compute this, and then I'll get an answer. So for example, okay, maybe just ignore this for now. Below I'll do an example. So suppose I have I can plug in any numbers I want. So let's just say x3 is 5 and x4 is 2. Just, any numbers. Maybe -2. Maybe that will make my life a little easier. And for whatever numbers I pick, I can plug it in and get a solution. So for these two numbers, I end up with okay, what do I get? I get 40 minus 25, 0, plus minus 14, 6, 0, minus 2. And this adds to, I mean, it's not important what the numbers are, but Okay, let's see, what is it? We got 26 minus 14, 5, and minus 2. So anyways, just as a side comment, the way that I can interpret this form of the solution is that I have these two so-called parameters, and I can plug in any number I want in the place of these two parameters. Whatever I plug in, say this, I can just plug it in and I'll get an answer. And this will be one vector which solves the original equation, ax equals 0 for this matrix. But I could have put anything here. I could have put x3 equals 2, x4 equals 17. And you plug it in and you get another solution. Okay, maybe I'll just say that much. But let me know if that actually answered your question, Sal. And otherwise, do ask a clarifying follow-up question. Okay, but let me erase this for now. Oops. Okay. So let me pause for a second. Here's another question. Well, it's kind of a follow-up question. So describe this solution set here. Describe it geometrically. So I'll give everyone here maybe a couple seconds to think about it, how you would answer this question if it was on a midterm, and then I'll give my solution. And if you feel like you know the answer, you can feel free to type it in the chat. But okay, so at least when I TA'd for this class, this type of question asks for two things. One is, well, maybe I'll write it down actually. So one is the dimension of the space. And the second is where does this set live? Or where does this space live? So what do I mean by that? Okay, once we have the solution set in this form, in this vector form specifically, the first question is, well, both are not too bad, but the first question is simple. It's just counting how many vectors there are here. So, okay, here there's 2. And so the dimension of this space will be 2. So this is a 2-dimensional space. Which sometimes is enough. But maybe what you're looking for is also that this means it is a plane. On the other hand, there's the question of where is the plane? So, for example, if instead it was a line, it's one thing for the solution to be a line in R2, and it's another thing for it to be a line in R3. Right? So that's kind of a question also of where does this space live? And okay, for these types of questions, the way I found that a lot of students were tripped up by this. The way I like to think of it is, if I take a single solution or a single vector in my set, then how many numbers does it have? How many entries does the vector have? So in this case, a single vector will look like something like this. here in this form. And so I need to count how many entries are there in here. And okay, there's 4. So that means it lives in R to the 4. So 4 entries in the vector implies that I guess it is a plane in R4. Or maybe let me write it this way to be more clear. Rather that, okay, the set is in R4. And so when you put the two things above together, you get that the answer is a plane in R4. Okay, so there's kind of 2 pieces here. Yep, at coleslaw on TikTok, 4 is the correct answer here. So in terms of describing sets geometrically in this class, there's 2 different things to keep track of. One is kind of the dimension, which, okay, kind of to jog memory, hopefully, this is related to the matter of a basis. So how many vectors would be in a basis? And the second is what bigger space does the set live in? And so that, okay, I mentioned, but I didn't write it down, but the way I like to think of it is pick a single vector from the set and then count how many entries there are. So it's going to end up being 2 pretty separate things to keep track of. But okay. Let me, maybe that's good enough for this question. Okay, I have another question here on linear independence. You can all, if you're already here, you can stare at the question and see if you can take some time, do some computations and see if you can do it. But otherwise, if you just got here, just taking a pause to say that this is our Linear Algebra Live office hours. And so I'm here from, well, at least until the end of the hour, and you're welcome to ask any linear algebra questions you have. I have a couple prepared, but this is intended to sort of function like a midterm review in case you have a midterm coming up. So you're more than welcome to type a question that you would like me to answer in the chat, and I'll be happy to do an example. At the same time, it's also good to mention that if you have another class that you need help with, you can scan the QR code. It should be in the upper left corner of your video screen, and that QR code will give you a full course schedule of what Chegg is doing this week with these live office hours. So maybe you're here for linear algebra, but you're also taking calculus. You can find out when they have the calculus review as well. Okay, so maybe I think that's enough time to think about this problem. So let's tackle it together. So the matter of linear independence is the question of, okay, maybe to review, this is a question of solutions to C111 plus C2 1 minus 1 2 plus C3 314 equals 0 0 0. Okay, so you're given a set and you want to know whether the solutions to this, whether there are more solutions to this than just setting everything to 0. Okay, because of course you can see that if I take C1 to be 0, C2 to be 0, and C3 to be 0, This will always solve it, but the question is there more? Okay, so the way we do this is once again by doing row reduction. This time the matrix is not in. Well, actually, first, I guess the first step is we want to take all these vectors and put it together into a matrix. So we do it like this. And then we want to see, is this matrix, well, we want to look at this matrix in row reduced form. Essentially, we want to see, are there any free variables or not? So if you already did it, you can put your answer in the chat. But okay, I'm going to be a little slower. So let me start here. So to do row reduction, I want to eliminate these two ones. So I get 1, 1, 3. I'm going to take the second row and subtract the first row. I'm going to take the third row and also subtract the first row. Oops, here. And I get, so here, what do I get? I get 0, minus 2, minus 2. Yeah, and then here I get 0, 1, 1. Okay, and then you can see that if you were to reduce this further, okay, I can divide this whole row by minus 2, but that would leave me with the same thing as this bottom row. So okay, I'm going to go a little bit more quickly and do this in one step. Well, actually, okay, let me just do it like this. So this is taking the second row and dividing by minus 2. And then I can subtract the third row from the second row. Okay, and the point is what? Well, actually, maybe since it's you don't have to, but maybe I'm going to go even more slowly and get it into fully row reduced form, just in case, just so you can see it in case you have a test question that just says to do row reduced form. I can now take the first row and subtract subtract the second row. Okay, now it's fully in row reduced form. And I just look at the pivots. If there's a pivot in every column, then the vectors are linearly independent. But here, there's no pivot in this third column, so it is not. So let me summarize. So for linearly independent questions, we can get it in row reduced form, and then if number of pivots is equal to the number of columns, then the vectors are linearly independent. But in this case here, no pivot in the third column. That implies not. Well, okay. I guess not linearly independent. Usually we just write linearly dependent. Okay, so that's how you would tackle these linear independence questions. You want to get into row reduced form and then count the number of pivots here. Okay, so this is it's very standard question. You should expect to see something like this on a quiz or a test. So, oh yeah, also at Jules from TikTok. I'm glad that you liked linear algebra. I guess it's possible that if you end up taking more math classes, then all these things will come up again. So it's good to always have a strong base for linear algebra. Actually, I think last week there's a lot of people taking numerical analysis, which were here in the audience, and it's good. It's good to see it applied in other settings too. Give us some motivation to learn. All right, I have a related question to follow up on linear independence. I will hopefully give us some intuition as to what it looks like when vectors are linearly independent or not. So here's a follow-up question. I have the same three vectors, and we want to, again, here's another describe geometrically question for the span of those vectors. And also, just to hit a point home, to compare to the span of these two vectors. So, okay. I'll give you all a moment to think about this. As a hint, it would be useful to have this row reduced form. Actually, I'll copy that down here. So the row reduced form of the matrix with those three vectors. Okay, what was it? It is 1, 0, 2, 0, 1, 1, 0, 0, 0. Okay. So with that in mind, give you all a moment to think about this question. So here's specifically two questions. Again, more specifically, what is the dimension of the span? And what space does the span live in? So if you know the answer, you can type it in the chat. Oh, see a comment from Richer Than Life on TikTok. Oops, I realized I misplaced the 1 as a -1 for the vector. Yeah, I feel like these, I think the downside of linear algebra is it's really easy to make these like random like arithmetic mistakes, which unfortunately can make your life a lot harder on a test. But yeah, it's just a part of this class. All right. So let me go over the solution for this now. Okay, if you have to look at the dimension of the span, okay, let me say that the dimension of the span is the number of pivots here. So dimension of span equals the number of pivots. In this case, it is 2. So actually it's here, it's also a plane. And then, okay, recall what I said for what space does the span live in? So first of all, the span is by definition the combination of the vectors that you're asked to find the span of. And so my trick for always getting the space that the span lives in is, again, to take a single vector from the span and seeing how many entries it has in that vector. So here you can take a single vector like this and see how many entries does it have. So here it's 3. And so that means that the span will live in R3. So, and the span lives in R3. Okay, but kind of have the second follow-up question. Compare this to the span of just the first two vectors. I have this here to illustrate a point, which is that if you were to do the same answer, starting with just these two vectors, okay, you would end up with the same matrix, but take out the third column. So if you can just kind of visualize this, you would just get this as the matrix. And then you would get the same number of pivots. And so the dimension of the span would be the same. So what that means is that this vector, adding this vector to the list of vectors, did not change the span at all. Another way to say this is that, okay, if you took the span of these two vectors, you get a plane. Okay, actually I didn't write that down, but let me write it. So it's a plane. So you can imagine, can you guys see? Okay, yeah. It looks like a plane. And adding this didn't add anything to the span, which means that this vector is already in the span, is already in this plane. So it's like geometrically that vector is already here. It's not like lying somewhere else. Okay, so, and you can kind of check that too. If you have, if I have, okay, how do I draw this? Well, anyways, you can actually see that the vector 3, 1, 4 is equal to twice the first vector, I believe, plus one copy of the second vector. 1 minus 1, 2. So geometrically, well, okay, yeah, that's what it should kind of look like is you're able to make this vector already just by using a combination of these two. So adding this vector to the span doesn't add anything. And my point in doing all this as a question, as a follow-up to this question, is that's kind of the picture you should have for linear independence, which is that if they're not linearly independent, like here, they're not, then you have a situation like this, where one of the vectors is already in the same like plane or line as the other vectors. Yeah, okay, maybe I won't say any more about that. Okay, so after this, I have a couple of multiple choice / true false questions that might mimic ones. So these are more like conceptual questions that you might see on a test. So I have a couple of those prepared. But in the meantime, let me just take another pause here and say, welcome if you have just joined us. We're in the middle of doing some linear algebra review questions, but this is it's an hour for you all to drop into this live office hours and ask any questions you want on linear algebra. So if there's a specific topic you need help on, then yeah, feel free to let me know and I can come up with an example on the spot and we can work through it together. Otherwise, if you need help with another class, You can always scan there's a QR code in the top left, which will let you see the whole schedule for the coming week of all of Chegg's live office hours. Also, there's a message from Yappington on TikTok. Is this easier than Calc 3? I think that is very subjective. I know people who think it's much easier than Calc 3, and I know people who think it's much harder than Calc 3. So I'd just say it's really different. I think it really happens to be, which class just kind of ends up clicking easier for you. Tends to be, I wouldn't say one is harder than the other. Okay, so here's a multiple choice question. So it's more conceptual. It's not a computation, but yeah, you might see some of these questions on your exam. So I want to go through a few of them. So this one says, if A is a 3x4 matrix, so call it 3x4, it's going to look like this. So you have 3 rows here and 4 columns. And the dimension of the column space is 3, then the number of solutions to ax equals 0 is either a 0, b 1, or c infinity. So you can think about it for a few seconds, and then I'll go over my solution. All right. So very good. Richer Than Life on TikTok says C with the explanation that the null space has dimension 1. That is exactly right. So, okay, how do we think about this? If I were to see this on a test, the first connection to make is that the number of solutions to ax equals 0 is related to the dimension of the null space. Right? The null space is exactly the set of the solutions to ax equals 0. And so, yeah. So the first thing to note is number of solutions to ax equals 0 is related to the null space. On the other hand, we are given information about the dimension of the column space. So we have info about the column space. And so the connection you need to make is this so-called rank nullity theorem. Well, it may be called something different in your class, but the point is that theorem, which says that the dimension of the null space of A, which I'll just abbreviate like this, plus the dimension of the column space of A is equal to n, where n is or for a m by n matrix. So this is a general. Let me scroll down. Number of variables. And so, okay, applying this here, we have that n here is 4, and the dimension of the column space is 3. So this tells us that for this problem, dimension of null A plus 3 equals 4. So the dimension of the null space is 1. And you have to also connect, what does that actually mean? How do we interpret that? That means that the null space itself is a whole line, which in particular means that you have a whole line of solutions. And so you'll have in particular infinite solutions. So this means a whole line of solutions. So answer is C, infinite solutions. Yeah, very good. All right, here's another one. This one is a true false. Suppose the matrix A has the form A equals, okay, and what I meant to write here is that the first column is 1, 2, 3, and the second column is 2, 4, 6, and the last two columns can be anything. So these stars mean any number. So true or false, AX equals 0 has infinitely many solutions. I'll give you all a moment to think about it, and before you can type in the chat if you think you know the answer, and I'll go over it in a little bit. All right. So let's go over this. So I think this question boils down to what does it mean to write the equation AX? And so actually, in general, okay, so suppose I have this matrix A. I have 1, 2, 3, 2, 4, 6. I got some numbers here. Maybe let me just write V as a vector, and here's W for another vector. And I'm multiplying this by X, which is it'll be a 4 by 1 vector, because this is 3 by 4, so I have to multiply by a 4 by something. Okay, so it's x1, x2, x3, and x4. This equals 0. And there's a couple interpretations, but one interpretation is that this product is the combination of the vectors or the columns of A weighted by x1, x2, x3, and x4. So, okay, more specifically, this is just equal to x1 times the vector 1, 2, 3 plus x2 times the vector 2, 4, 6 plus x3 times whatever this is, so whatever these numbers are, plus x4 times w. And if I want to solve this to be equal to 0, note that I can just take, to solve for this equals 0, I can always take x3 equals 0, or wait, I meant to say this. take x3 equals 0, x4 equals 0. And then I can always take those to be 0. And then, for example, I can take something like x1 is minus 2 and x2 is 1. And then x1 is minus 2, x2 equals 1. So hopefully you see that would make it 0, right? So it would, taking x3 and x4 to be 0 makes these go away. And then when x1 is minus 2, okay, it's like I have minus 2 here, and then 1 here, then it will cancel all these numbers out, and I'll end up with 0. But actually the point is that, okay, that's going to give me one solution. And actually anything I take where this is minus 2 times whatever this is will also give me a solution. So I actually end up with an infinite number of solutions. It's like I just need this or this to be weighted minus 2 times whatever this is weighted. So in particular, but we can also take x2 or x1 to be, okay, let me write it like this. We can always take x1 to be equal to minus 2 times x2. And this gives us infinite solutions. And so, okay, the answer here is true. All right. That was a bit of maybe a different question than one you might have seen in class. Well, hopefully it was. Want to get us thinking more about how to interpret different things in these matrix equations and stuff. Yeah, so it's good to know that how do we actually interpret a matrix product like this is as a combination of the column vectors. And if we see that, then we can see how we might get these infinitely many solutions. All right. I got one more true false question. And yeah, so, okay, I'll read it. Well, it's true or false. We have a 3x6 matrix A. So a 3x6, 3, 6 matrix A, such that the dimension of the null space is equal to 2. So as a hint, this is going to be similar to the previous rank nullity question. But it's good to see a question like this as well. So I'll give you all a moment to think about it, and you can type in the chat if you know the answer. Also, just to plug again, that if you need homework help for a different class, Chegg has many more of these live office hour streams. So this one is just linear algebra, but there's many more classes, and you can see which classes are available by scanning the QR code in the top left corner. And also, that'll also give you the whole schedule of like when each class is having their office hours, and hopefully it'll be good, a good place to study for your midterms. All right. So I think that should be enough time. Can let me know if you think it's true or false. So this is how I'll think about it. We know that, again, by rank nullity theorem, well, okay, let's assume that it's true for now. By the rank nullity theorem, we get the dimension of the null space of A plus the dimension of the column space of A is equal to n, the number of variables, which here is 6, and that implies, okay, just by plugging this in, that the dimension of the column space is 4. Okay, is 6 minus 2 is 4. But, okay, now we need to think, what is actually the dimension of the column space? Okay, the dimension of the column space is equal to the number of columns with pivots. Well, actually, that's a little confusing. So let me instead just write is equal to the number of pivots But what is a pivot? A pivot is the first number of a row, which is also a 1. And so here we only have, if it's a 3 by 6, then we only have 3 rows. So at most we can only have 3 pivots. So, but 3 rows implies at most 3 pivots. And so that's impossible. We cannot have the dimension of the column space be 4 and yet have at most 3 pivots, because the dimension of the column space is supposed to be equal to the number of pivots. So, okay, in conclusion, we have that. Okay. Thus, can't have the dimension of the column space be 4. So the answer is false. Which I also now see that Richer Than Life on TikTok got it exactly right. That's false because you get 4 for the column space, and that is not possible. All right, very good. All right, this actually took a little bit longer than I thought. So I feel obligated. So last week there was someone that asked me to do a question on the Cholesky decomposition, which admittedly wouldn't really be for a linear algebra class. It's for a numerical analysis class. But I think it would be worthwhile to go through it and have it on the record, because I promised him I would do a question like this. Oh, I also see, though, we have a question. Can you go over complex eigenvalues and eigenvectors? Well, now I don't know what I should do. Okay, let's see. All right, I think I should prioritize a linear algebra question rather than one from a numerical analysis class. All right, I also have 5 minutes left, so I'm just going to try and give a quick example and go through it. So, example for complex. So, okay, first of all, a complex eigenvalue / eigenvector. An eigenvalue should, if it's a real number, it would correspond to stretching a vector, right? If you have an eigenvalue of 2, it means that when you multiply the matrix times this eigenvector, you get twice that vector back. That stretching geometry doesn't have any meaning when the eigenvalue is imaginary. So instead, the geometric interpretation is that it corresponds to a rotation. So, okay, that's enough for that. Let me now do a problem. Let A equals 0, 1, 1, 0. And let's compute the eigenvalues. Slash vectors. So, okay, as usual, as for the real case, we look at A minus lambda times the identity. We get, we get minus lambda, 1, 1. And so the determinant of this gives us what? Lambda squared wait, well, actually, maybe I chose bad numbers, that this won't give me a complex one. Okay, let's do, let's add a minus 1 here. So here we get lambda squared plus 1 equals 0 for the determinant. Okay, so we solve this. Usually for a complex question, you would use the quadratic formula. But here I gave myself an easier question. So here it's easy to solve that. Lambda is going to be plus or minus I. So let's say lambda 1 is I, and lambda 2 is minus I. And then we plug it in. We have here, we get, okay, for lambda 1, we get minus I minus 1, 1 minus I. And I want a vector v such that this is equal to 0. So that will give me my eigenvector. And it turns out for a 2 by 2 matrix, if you've done this correctly, you kind of get a shortcut, which is that I can always take v to be equal to this number as the first entry and negative of this number as the second entry. And you can check. You can just check this, okay? So here you would get for the first, you want to take this row and multiply it point-wise, entry-wise by this. You would get I minus I equals 0. On the other hand, for the second row, okay, so you can check. Okay, here you get I minus I, which is 0. And on the bottom, you get minus 1 minus I squared, which is negative 1. You get minus 1 minus negative 1 is also 0. Okay, so you get, you can check that this works. So the trick I'm saying is, if this is some matrix like this, then you can take eigenvector as minus, or okay, I wrote it as b minus a. So, okay, I got 1 minute left. Okay, let me just, yeah, well, this will give you the eigenvector for lambda 1, and then you can get the, which is here, you can get the eigenvector for lambda 2 similarly. So, and also note that this trick really only works for 2x2 matrices. Okay, if you had a 3x3 matrix, you would have to do the grunt work of taking this and doing the row reduction to solve for the matrix equals 0. But okay, I'm out of time, so I hope that helped a little bit. Otherwise, you can feel free to come back and ask again next week. But that'll be all for today's Linear Algebra Office Hours. If you need help for other classes, please check the schedule on the top left. There's a QR code you can scan for the whole week for Chegg's classes. And otherwise, we'll be here next week, 7 p.m. Eastern or 4 p.m. Pacific time. So yeah, good luck with your studying, everybody. And